Okie dokie. Let's get this show on the road. Due to various vacations, staffing changes, and things beyond our control, you guys get me again for today. My name's still Ben Dolan. I still work over there. Today we're going to talk about computer numerically controlled machining, or CNC machining. This presentation is going to be quite a bit shorter than the last one, so you guys can go enjoy the weather. Big thanks to Steve Weinstock. He's going to be holding your practicum. He's going to take you guys all through running the actual machines here on campus. If you don't know, there are CNC machines scattered around throughout the engineering department. There's a whole bunch of them, of manual mills and lathes in the basement of the engineering tower. We have a 4-axis mill. In my offices, we have a 3-axis router, and I've seen others here and there. There's some over in Cal IT too. There are some in the building behind us. So it's really going to be about who you know and who gives you access to which tools. Also, thank you to Horacio Akido, Kevin Gubitz, Brian Eastman, and Charles Murray. This presentation I basically stole from little bits and pieces of theirs. So if you don't like it, you can blame them partially. So history. All right, it's been around a fair bit of time, certainly predates us. Traditional manual milling, basically early 1800s. On the right there at the bottom, you can see a mill that was from 1818 and is credited to Eli Whitney. There's some debate if it was actually his and if the year was actually 1818, but that's what the slide says. And then lathes. Lathes have been around for a long time. So one of the earliest known lathes was from this carving that you see out of stone. And it kind of looks like the old Boy Scout rub sticks together to make a fire. Same idea, but you've got one person using a band, probably of leather or something, to quickly rotate a probably wood piece, and the other person using a cutting tool to shape it. And that puppy is from about 1300 BC. So lathes have been around quite a bit longer than the mill. So what really moved us from manual machining to CNC machining? That's national defense dollars, right? Anytime you can get the defense to say, hey, we need this, that technology is going to move quite a bit faster because they can put all sorts of money behind it. So it really kicked off after and around World War II. And immediately after World War II, they were looking at, okay, computer numerically controlled machine, what can we do? And it used to just be called a numerically controlled machine. And we added the computer part around 1952. And that first machine, I'm not certain that the one on the bottom right is actually the first machine, but they ran off of old punch cards. So you would have tape cards or punch cards, and with a whole bunch of little pinpricks in them, and the machine would read that and translate that to instructions. They were apparently not terribly popular. You had generations of people that were used to manually milling everything, and then now you're telling them, hey, you got to use this computer and this long tape with a bunch of holes punched in it to do what you're already doing. So it took a while to catch on, and it wasn't until the 80s when we got really closer to what we have now as CNC machining. So why would we do it? It is a lot of work to manually mill a fancy surface. So this helmet that you see on the right, this is a CNC'd helmet out of billet aluminum. It was done as a demo for either a 5 or 7-axis CNC machine. It is one of the more impressive CNCing videos that I've seen on YouTube. If you guys get a chance, look it up. They kind of cheat. They don't show a lot of the finished work, and they just kind of Martha Stewart it, and poof, there it is. It looks great. So why is it great? Having many axes available can simplify part holding. and reduce the setup. So if you've only got a 3-axis mill and you've got a shape that has all sorts of convolutions and weird, nice, smooth surfaces, it can be a lot of work to figure out how to hold that shape so that you can machine one side, then rotate it so you can machine another side or whatever. And the more you machine away, the more difficult it gets to hold. So you consider if you made something with a spherical dome on one side, and then you had features on the underside of that dome, you got to think about, okay, if I machine that surface first, and I got to flip it over, how do I grab a dome? It's really difficult. So you got to do a lot of thought about how you hold these things that you want to machine. Another huge reason, repeatable, precision, and accuracy. This is why you go to CNC machining, because you want to repeat it, you want it to be precise, and you want it to be accurate. Those are two different things. We'll show a little picture of that later in case there's any confusion. And then unmanned processes. One person can run a whole bunch of jobs at the same time. So if you've got production level work and you know I need to make 100 of something, you know, that's not something that you're probably going to mold. It's probably something that you'll cut. So you machine it. So you do the first one, you figure out all the steps. Once you nail that down, you hit the green button and it cuts the next one. It spits the part out, you hit the green button, cuts the next one. This is really huge in the CNC lathe department, where they're making hundreds or thousands of pieces, where cycle times can only be a few seconds sometimes. And they'll just knock them out all day. And you check every 10th or 100th one, make sure it falls within spec, adjust your tools, and keep going. So why do we want to do it? So if you've got a chunk of material on the upper left, and you want a coniseg or a knee implant or the space arm or some sort of impeller, you got to get from that block of billet to one of those shapes. So various fields that CNC machining impacts, of course, aerospace, automotive, medical, nautical, architecture, commercial stuff, art, many others. Pretty much anywhere where you need a lot of precision and repeatability. And you start with a block of something and you got to cut down. So unlike our last lecture where we grow everything up, here we're starting with a nice piece of stock and removing what material to get to what we need. One of the advantages here also is the material is a known material. So if I specify TA64 ALV, I know that I'm going to get that. Or if I want PEEK or ABS or acetal, doesn't matter. I start with a block of it and I cut it down. It also helps with traceability. So in some fields, like aerospace and medical especially, it's really important to know the life of that material before it gets to whatever use. So a lot of times, if you order traceable material, it comes with a document that says, okay, this is what this material is, this is where it came from, and this is the life that it's seen. So if you've got an F-15 and it crashes because the wing fell off, they can go back and say, why did that wing fall off? And they look at that material and say, look, where's the material data sheet for this thing? Where's its history? They go, I don't know. That's a problem. Or if you've got implants in humans, and you find out that, oh, look, that PEEK skull implant has collapsed. Why did it do that? I don't know. Let's find the paperwork. So super important. So they can be easy to run and program the second time. The first time, it's typically a lot of work. Okay? As you get better at it, it gets quicker, of course. But I can guarantee that that helmet was ugly, ugly to program. They can be extremely reliable. You can knock parts out all day, over and over again. You can change programs pretty quickly. A lot of things now, they're either fed through a serial cable if they're kind of older, and it's a huge program, or they can be on a USB drive. Some of the machines around still use a floppy drive. Numeric controlled machines don't take a lot of data. So it's literally just a text document that is a list of commands. And they are all coordinates and machine commands. So you may have heard G and M codes. Those are codes that tell the machine what to do. So you give them G and M and your X, Y, Z. Or if you've got 3, 4, 5, 6, 7, 8, 9 axis machines, you get C axis and A axis and all these other axes. They get kind of funky. They can be very safe to operate. So a lot of traditional machines, no guards or anything like that anywhere. So if you've got your nice long ponytail and you're operating a lathe and it happens to scalp you, that happens. You know, I worked with a machinist in a mold shop, and he came from, he'd been in the CNC business for about 40 years, or in the machining business rather. And he worked in a shop that did very, 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 very large things. So if you think about naval vessels, there's a propeller shaft that could be 450 plus feet long. And it's got to be round because that puppy's spinning and it's got a huge load at one end. So they need to be pretty darn round. So he described to me lathes where you actually rode on top of the tool. So these things are large enough that I would sit on this little table with a giant tool going along this trailer basically. And he said the way that you tightened the tool was you took a 4x4 piece of wood and you pulled on it and pulled on it and pulled on it until it went crack. Okay? So super high precision right there. But it was good enough. So he said there were a lot of friends with, you know, partial fingers. And a lot of that's changed. I've still got all mine, and they're all OEM. What else? So the picture on the bottom there, you may have seen this before. It's accuracy and precision. Accuracy or precision, and neither. So you always want accuracy and precision. If you're precise and not accurate, that means you did everything great over there, but you should have been over there. You know, you can be accurate and not precise, which means on average you did pretty good, but nothing was really that close. And then if you're missing accuracy and precision, you just failed at life. So important things to consider, obviously the cutting tools. Like, what are you doing on a CNC machine? You're cutting stuff. So the most important part, the things that you cut with. So hugely important are the diameter. Okay, you can't do really fine detail with a giant tool. The shape of the tool at the end, whether it's flat, ball, bullnose, tapered, a chamfering tool, a rounding tool, a filleting tool, whatever. The number of flutes. So if you can see the mouse cursor, this guy only has 2 big flutes versus this thing has a whole ton of little flutes. And that controls quite a bit of how it cuts and how the chips evacuate and so forth. The tip geometry is ridiculously important. So it's not enough that it's just round or square. If you're using some sort of indexable end mill cutter, which basically looks like a chunk of metal with a bunch of little blades screwed onto it, there are companies whose entire livelihood is based on the shape of those little blades and the material that they cut. The material itself of the tool, whether it's high-speed stainless, carbide, some cobalt crazy thing, and then coating. As well as geometry, coating is hugely important. So whether it's some sort of nickel or cobalt or bare carbide or titanium alumina carbide or titanium aluminum nitride, there's just this whole alphabet soup of different coatings that are specific to the material that you're cutting. So aluminum and steel don't like the same materials to be cut with. Titanium, Inconel, coppers, they all like different things. So if you're doing a soft sticky metal, you want one sort of coating so that it doesn't stick to your cutting tool. If you're doing a high temperature one, doesn't matter. There's somebody who did the research to figure out the best way to cut that material. So also take into account what you're cutting. You know, if I'm cutting stainless steel versus 4130, they're going to behave a little differently. Aluminum and magnesium, and since you don't want to use coolant that's water-based on magnesium. You know, magnesium doesn't like water. Various other things. How you're cutting it, if you take it lightly, it's one sort of thing. If you really dig in there and pull out huge chips at one time, entirely different. So coolant type, if any, there are lots of specialized coolants. Some of the older coolants were actually animal-based. You had various oils and fats and things like that. They smell terrible. They turn into like floating chicken if you let them sit too long. There's water-based and oil-based coolants. A lot of people for injectable stuff will use air, and some of them use vortices to cool down the air so that it's below zero. And then there are ways that you can do it without coolant. I've seen at trade shows ceramic tools where they just dig it in, and there are sparks and all sorts of horrible things that you typically never want to see, and that's where that tool is happiest. Undesired surface finish. Do you want it to look good, or is good enough? Okay. So there's roughing tools and finishing tools, and it just depends on how you're going to do it. So once you've got your tool, feeds and speeds. These puppies are super important. So there are plenty of old school tables that you can look up. There are online widgets and calculators and things like that. And a lot of programs now have them built in. And it is, how should I say it? There are general rules of thumb where you look at the diameter and you look at what your machine's capable of, and it'll get you close. But depending on your material, the geometry of your tool, the life of your tool, either how much you want to get out of it or how much you've already sucked out of it, how light or aggressively you're going to machine, whether you have coolant on or not, and then what you're willing to sacrifice in terms of tool life, material quality, surface finish, time, etc. All these things will dictate how fast and how hard you can run that machine, as well as the machine itself. You know, if I've got my little 4-axis mill up there, I can't treat it the same as, you know, a $100,000 professional quality, you know, part that would machine something like this. You know, I've worked on mills where I could walk around inside. I can treat that mill with a lot more go than I can with the mill up there. So, and again, choosing the right tool for the job. I'm not sure if you guys have had it yet, but I believe somebody was doing a talk about micro machining. So you can micro machine and you can go all the way up to very much macro. The boat industry and aerospace, as well as guys that make the giant windmills, they have some of the largest machines. So bottom right corner, that's a guy standing inside this mold. I wanted to say that was a boat hull, but it might also be a blade for a power plant. That machine, if I remember reading right, is about 150 meters long. And it's for doing full-size parts versus the stuff on the left, just little tiny doodly dads. I have no idea what they are. Axis-wise, 2.5 to 9. So 2.5, think plasma cutters, routers, things like that. So you've got your XY control and there's some Z, but it's typically a fixed depth. Okay. 3-axis means you can do surfacing and things like that easier. 4-axis means you've brought in rotation. 5-axis, there's another rotation. 6, 7, 8, 9, you've got so many things going on, I have no idea. So if you think about degrees of freedom, right, we're used to 6. You've got all your translations and your rotations. So once you get above that, you're starting to include different movements of the heads. So think more like robot a lot of times, where they can do crazy things, and they have live tooling. So while this arm's moving over here, the head at the end of it's wiggling around, and it's spinning in different directions as well. Allows you to get really, really complex shapes. So now we're going to go to the quick part. I believe Steve will be taking you guys through this. Again, Steve's the one that's doing the practicum. So you design your part. It doesn't really matter what you design it in, whether it's Rhino or SolidWorks or Autodesk software, whatever. You're going to export some sort of solid body or surface file into a CAM software. So many of you may have heard of Mastercam. There are hundreds of others. We've used stuff called Visual Mill. There's SurfCam. I can't even think of some of the big ones right now. But you find one that you like and that you can afford. The afford part gets just silly. There are 6-figure CAM packages very quickly. So simulate the machining, right? You've got this fancy computer. Make the computer figure out how to machine it the first time. You know, do all your paths, test it. See if it smashes into itself on the computer before you smash your actual tool into it. Save yourself the time and the money. Get that data onto that CNC machine one way or the other. Whether it's a floppy disk, USB, serial, Ethernet, whatever. Just get it over there. Load that code. Depending on how you're cutting, maybe you need a sacrificial plate. So let's say you're cutting a like a gear. You've got your piece of material bolted down, and you've got another piece of material under it for it to sit flat on. And you want to machine all the way through, and you don't want flash or anything crazy on the ends, and you don't feel like turning it over to try to align it all again. Just put a sacrificial plate down. You can cut through it. That way you're not cutting into that table. The table of the CNC machine is not something you want to replace, and you avoid cutting into it at all costs. So one of the most frustrating parts that I've had to do in teaching students how to CNC machine is setup. If you do a poor job setting up, that's going to translate throughout your whole process. So take the time to set it up correctly. I'm a huge fan of using dial indicators. You can also use an edge finder. Edge finder will get you close, probably to within 1/1000th of an inch. Versus a dial indicator, you can probably get to within 1/10,000th of an inch, or about 2.5 microns. So depending on how much you care and how rough your stock is, you know, an edge finder is often enough. But if you're working in a mold shop and you knew that that mold has to be accurate to within less than 1/1000th, and it's going to be several $1,000s to machine it, the last thing you want to do is make one mistake in the beginning that scraps thousands of dollars later down the road. So once you've figured out where your material is, determine an origin, okay? I'm a big fan of, if I'm working with rectangular stock, I put it in the middle on the top. Other people like it in the upper left corner, whatever. Pick a convention and stick to it, okay? Don't go changing your origins around. That will just create all sorts of nightmares for you down the road. Because imagine, okay, I've got a CNC program, I've saved it on my thumb drive, put it on the shelf. 5 years later, the guy calls back, wants another one, so I pull it out, and I assume my origin's over there, but 5 years ago I liked my origin right there. So I go to cut, and I just machine straight through the table or through my vise or whatever. That would be bad. Bad, bad, bad. So set it up. Z height, incredibly important. So generally speaking, Z, it's always up for us. the origin, it's the top of your surface, okay? However, every tool you have has a different length, so they all have different Z's. So these are your offsets, and you have to set all the offsets for each tool that you're going to cut with. And you do that at the beginning, okay? Or you leave a little piece somewhere over there that you can touch off on later. But if you have crazy different lengths, you machine some and they're like, oh, I forgot to figure out the length of the other one. There's now no surface for you to touch off on. So the Z height is unknown. That would be bad. There are tool offsetters, which are little blocks with a little tiny lever on the top of them. And the machine would come down and just touch it, and then that reports back to the machine where it is. Those are nice if you can afford one. They're also kind of cheap. Another way to do it is with a gauge block, which is a highly calibrated little piece of metal. And you set it on top of what you're machining, and you bring the machine down until it just registers enough friction that that gauge block will move at one step, won't move at the next. That's your new Z height, and you just account for that extra thickness of that gauge block. That's the method I prefer. A lot of people also use a sheet of paper, and they know how thick that paper is, and if you screw it up, it's just paper. Or you can use a height gauge, depending on the machine and how you've got it set up. Again, so long as you always do it the same way and you're consistent, it doesn't really matter how you do it, so long as you get it to work for yourself. And then you input all that information into the computer, because that computer is going to reference that information over and over again, so it needs to know it. And this is especially true if you have a giant tool changer, something that holds 10, 20, 30, 60 tools. You set them all ahead of time, put it in the computer, hit run. It'll change tools all day for you without you having to come back and measure stuff. So if you've got a machine with a manual drawbar, something like that, you put the first tool in, you tell it where it is, where's home, and you run your simulation if you want. But generally, you run it, you've got your hand over the E-stop, okay? And it's also not a bad idea the first time to watch your speeds, because these machines will move quite a bit faster than you can respond. So I've seen it on multiple occasions. Somebody figures that, oh, X0, Y0, Z0 is over here. And they do a rapid movement with the tool, and that tool just tries to dig straight through the material. You get your Z wrong, and the machine doesn't care. It's just trying to do what you told it. So if your hand or the vise or the machine itself is in the way, it's still going to try to get there. You can make extremely expensive mistakes extremely quickly, and once that tool hits, it's done. You can't unscrew that. What else? Run the program, hand over the E-stop. Once you've got that all figured out, and you've run that thing the first time, go ahead and let it run again. You can pump parts on from there on. You know, hit the program, let it run, go work on your next program in the office. And a huge thing on machining is your ears. You're listening for the way that it's cutting. After a while in a shop, you know exactly what it should sound like. You can listen and know the load. You can know how the chips are coming off. You can see if your coolant ran out, all sorts of crazy things, just by the way it sounds. So that being said, protect your ears. Okay, safety gear, extremely important. You know, you don't want to have dangly necklaces or watches and long sleeves and safety gear. Protect your eyes, protect your ears. Wear gloves. Always important to take care of you. That way you can keep doing what you need to do. So after that first tool's done, you go to the next tool. So maybe your first tool is a rough, your next tool is a slightly better finish. You want to run a smaller tool to get into the corners, things like that. And you keep doing that over and over. Once it comes off, you get to do your secondary or tertiary machining. This is the finish work. Maybe you got to clean up the backside, or maybe you're doing something that was a mill and drill and a turn operation. So you have a lathe and a mill working together. It doesn't matter. You just keep going until you're done. And then lastly, cleaning up, super important. Okay, you don't want things rusting in your machines. You want to take care of the ways. The ways are the things that everything moves on. You don't want little pieces of metal stuck under them and then rubbing and rubbing and rubbing. It'll destroy your machine. And then you'll lose the accuracy and precision that you're trying to get. And then in the end, you've got your part and you're done. So we're done. Any questions I can answer? Okie dokie.